This video is for assignment number 2 in Unit 5, and I'm going to solve an example on this using one of the other methods that are explained in the notes. If you've had a chance to look at the Unit 5 notes and a couple of the slides that provide some additional tricks and tips to balancing equations, one of those indicates treating polyatomic ions as an individual rather than counting each element individually in a reaction. So on example C, I'm going to use this method and show you how it works. I've underlined in example C a couple of polyatomic ions that exist. On the reactant side, the OH is the polyatomic ion hydroxide, and the PO4 is the polyatomic ion phosphate. And one of the things to keep in mind of when you're using this method is that it works for times when the polyatomic ion shows up on both sides of the reaction unchanged by its formula. So the OH hydroxide ion on the reactant side shows up again on the product side with the same formula OH, and phosphate PO4 shows up on the reactant side and the product side without a change in its formula. Now, if you'll notice on example E at the bottom of the page, one time when you might not want to use this method, we have the polyatomic ion nitrate, NO3, on a reactant side of the equation. But when you find the nitrogen and oxygen formulas on the product side, even though one of them still is NO3 nitrate, you also see an NO2 equation or formula. And so that nitrate that was present on the reactant side actually went through some changes and separated into a couple of different formulas as a product. And so you wouldn't want to use this method on example E. But going back up to C, we're going to balance this without separating them into every individual element and just keep the polyatomic ions attached. So when I split this equation at the arrow and start counting, I'm going to count the objects, each of the ions. In this, we have potassium ions. There is the hydroxide polyatomic ion. You have cobalt, and you have phosphate, the polyatomic ion. And I should find each of those ions on the product side as well. We have potassium, the hydroxide, the cobalt, and the phosphate. So when we're counting these now, we're just going to count the ions. And for potassium, in potassium hydroxide, a 1. And there's a total of this hydroxide ion without parentheses or numbers outside those parentheses. Means that we just have one of those hydroxide ions. For cobalt phosphate, the subscript 3 for cobalt, and this PO4 in parentheses, the 2 indicates that there's a total of 2 of those polyatomic ions, the phosphate polyatomic ions. On the product side, count again, we have 3 of the potassium. This phosphate, which is not in parentheses, means that there's only 1 of the phosphate ions. For cobalt hydroxide, cobalt has a 1, and this hydroxide in parentheses and a 2 outside says that there are 2 of the hydroxide ions. So to balance this, we need to get all of the ions on the reactant and product side equal in numbers. I'm going to start with the phosphate ion. With 2 of the phosphates on the reactant side, I know that I need to have 2 of these phosphates as a product. I do that by putting a 2 in front of the formula for potassium phosphate. Distributing the 2 to both the potassium and the phosphate, change the numbers to 6 potassium and now 2 of the phosphate ions. For cobalt, with 3 cobalts as a reactant, I also need 3 cobalt ions as a product. I can put a coefficient 3 in front of the cobalt. That 3 distributes to both the cobalt, giving me 3, and the hydroxide ions, where there was 2, now there's 6. So I've balance the phosphate and the cobalt to get 1 and 1 potassium and hydroxide to become 6, or to balance with the 6 products, I can put the coefficient 6 in front of the potassium hydroxide. That changes my potassium number from 1 to 6. It also distributes to the hydroxide ion, giving me a total of 6 hydroxide ions. Again, no change was made to the coefficient for cobalt phosphate. That does indicate that there's 1 molecule of cobalt phosphate. So 6 of the potassium hydroxide molecules react with 1 of the cobalt phosphate molecules to produce 2 of the potassium phosphate molecules and 3 of the cobalt hydroxide.